research program, and the emphasis is it's a research program. 5G is being deployed commercially around the world. This is starting to tackle the challenges, the opportunities, and some of the convergence of technological, societal, and a range of other aspects. Flagship was established with 251 million euros, so a quarter of a billion euros, not a bad start, focused around a university in Oulu. And Oulu, for those who've ever been to Finland, well, it's known as the wireless fen. That's the heart of R&D for mobile communications in Finland, and has been since mobile communications was a thing, working with Finland's equivalent of CSIRO, the VTT, with Nokia, but now also with global university and industry partnerships. The main focus are wireless connectivity, devices and circuits, distributed computing, and services and applications. And that tiny little postage stamp picture in the top right-hand corner is the Scientific Advisory Board back when we could actually travel to Finland. The goals of the flagship are to get 5G into reality, support companies in finalising the 5G standard, because of course today is not the end of 5G, 5G will evolve, and carrying out technological and system pilots, creating and co-creating the fundamental technologies, and speeding up dependable, robust and secure digitization of society. And that's being done in conjunction with 5G test networks in Finland and in other parts of the world. The collaboration is now genuinely global. It started out as a Finnish activity. Now, this is the first difference about 6G compared to 5. It's not just about moving the bits. We have for quite some time talked about the coverage, the capacity, the availability. 5G talked about latency, and it talked about reliability of delivery. But now we're talking about all user-specific computation intelligence may move to the edge. The centralization of networks is no longer an option. The ability to offer centralized planning or optimization or even delivery in any way, shape or form instantly creates a bottleneck if we've got so many more devices. And the integration of sensing, imaging and highly accurate positioning capabilities with mobility opens up many new applications. But it also starts to drive this issue of trust. Can I trust the service that's being delivered to me? Because it goes through so many different stages, which are so different, and each one of them potentially compromisable. And privacy. If my physical location or what I'm looking at or my blood pressure enables a service to be delivered to me, now all of a sudden I've got brand new elements of privacy that I need to consider. And of course, all of that movement of data means not just trust, is it delivering what I expect, and privacy, is my personal information being protected, but also very complex interactions around cybersecurity. The other aspect is that the business ecosystems will change, and change in quite a fundamental way. We have historically had mobile operators who are centralized control, planning, optimization, billing systems. Over the course of the Gs, we had virtual mobile operators. And as we start to think about consumers buying their own picocell or femtocell and becoming producers, the potential for a business case shift starts to change again quite significantly. And if we are truly talking about as ubiquitous as possible for availability and generation of data, consumption and generation of data, and more of that data being used to create value, whether it's an optimization of a service or it's the service itself, who we think about as the end users or who has the assets starts to change. It's not a centrally controlled set of pipes anymore. And who does that matching of need with service or with demand for availability also starts to change. And then when we think around who actually needs this service from not just the matching perspective, but the end user, it suddenly starts to change. So who's using the service means it's no longer just a mobile phone user, a subscriber, an end user. It's now a data center or a facility owner or the edge cloud itself or a content provider or the government or the public sector or a national regulator. The matching can be done in a range of different areas now, as opposed to it just being the mobile operator or a virtual mobile operator. So a broking or bridging provider, a network resource broker, a data broker, a management service provider, a digital twin provider. And then ultimately the assets come from end users from machines, from enterprises, and from the public sector. Each one of those you could contest and break down, but as a high level, it starts to shift the thinking away from there are certain silos being enabled or certain sectors being enabled and certain controlling factors. And another one of the really interesting evolutions of thinking is towards the paradigm of local operators. So with the transition to higher frequencies and increased reliance on indoor networks, more and more of the equipment potentially is owned and or operated by someone other than the Telstras or the Optuses or the Vodafones of the world. The ability to share physical real estate, to share network resources, to share masts, to share locations, will inevitably be driven by the need to deliver so many more different services through so many different stakeholders. All of this that starts to add up to driving the paradigm of a local operator. So the technology, the data, the competence, and the cost all start to drive towards localized operation, potentially coordinated through what we would call a more traditional mobile operator. But that role of the operator may well become more of a broker than actually doing the operation in sense, with more and more of the transmission, the consumption, the matching and the demand and identification of customers and even the billing being done locally by micro operators or by aggregators in different sectors for different reasons. Now we start to get down to the brass tacks of what we think 6G might need. And as mentioned, every time we're contemplating the next G, we say, okay, well, let's make it 10 times what we did the last time, or 1/10 of what we did the last time, or double something. In the world of research, if you do an incremental gain, no big deal, your paper does not get published. If you add a 0 to it, then you're in a different ballpark, in a different order of magnitude. You will undoubtedly need to go through different challenges to achieve that. So it's far more likely that it's a research outcome. Now, we talked historically about coverage, capacity, and availability. We now in 5G talk about latency, we talk about jitter, and levels of reliability. And as we start to dial those up in anticipation of new data-hungry services, new context-specific services, then the needs start to also go up quite substantially. So mapping some of those issues of latency, jitter, link budgets, 3D mapping fidelity, position accuracy, cost KPIs or energy KPIs, then we can start to talk about, on the left-hand side, radio latencies below 0.1 millisecond, 20-year battery life, 100 devices per cubic meter, 10,000 times traffic increase, a maximum outage of out of a million outage, maximum 1 out of a million outages, 10 times more energy efficient, and accuracies for positioning indoor 10 centimeters, outdoor 1 meter. And peak data rates, the headline number of between 100 gigabits per second and a terabit per second. They just seem like numbers. The moment you start to talk about radio latencies of 0.1 milliseconds, that has a fundamental impact on how you design a network, simply due to the propagation of the speed of light. And then you add latency to processing, it means all of a sudden your architecture changes completely to guarantee 0.1 millisecond. If we talk about positioning accuracies of 10 centimeters indoors and 1 meter outdoor, again, there are some fundamental differences the way you either do collaborative positioning or the waveforms that you use if you're relying on the physical radio propagation structures. And if you talk about data rates of a terabit per second, you are automatically in the range of very exotic materials, very exotic waveforms, and very exotic transceiver structures. As research challenges, they are great to set a good challenge, but they only really make sense if you're really trying to talk about a practical next step, if they line up against business needs or against societal needs. And that's where we start to think about some of those other factors which are converging factors. I'm actually a radio guy way back. It's actually the only thing I know anything about whatsoever. And so I thought I'd spend just a little bit of time just talking about the radio spectrum for being contemplated for 6G. We know that radio spectrum is possibly the most valuable thing that we can't touch. We know that during the world of 3G, people went absolutely crazy buying the right to propagate, the right to radiate, spending tens of billions of dollars for little bits of spectrum. We also know it gets harder to actually get signal through as the frequencies go up. And it's harder and harder to find contiguous blocks of spectrum as we move through areas which, whilst relatively large in absolute bandwidth, become relatively modest when we think about the carrier frequency or when we think about the ambitious data rates. So there are a couple of things about spectrum which are worth contemplating. So not only are we talking about moving higher up the band, that's inevitable, and that has implications for propagation distance, but it also means we're no longer saying we just need a contiguous chunk of spectrum. We are willing to take a bit here and a bit there and a bit there, noting that as we move up into those more exotic frequencies, more absolute bandwidth is currently available. But we also know that different services will rely on very different parts of the spectrum because the way the signal propagates is very, very different at 400 megahertz versus 90 gigahertz. We also know that the materials we need, the antennas we need, the physical aspects of a device or a handset or any sort of radiation we need fundamentally change as we move up. And I couldn't go past that previous slide without just doing a very quick recap of what we know about attenuation of radio signal. And for those of you who've looked at the signals beyond the low microwave bands, beyond the 3, 5, 10 gigahertz range, when we start talking about 10 to 30 to 60 to 100, we start to get some really interesting pushback from nature. We know that we have an H2O absorption area at 22 gigahertz, so well beyond the ISM bands that we run microwave ovens on. But we also get some oxygen absorption, really substantial oxygen absorption around 60 gigahertz, and that's been really interesting for short-range communications. And it goes on and it goes on with some really interesting absorption lines associated with some fundamental molecules that we deal with every day. And as we look further out, we'll also see nitrogen and various other absorption areas. So just saying we'll just keep dialing up the spectrum, dialing up the center frequency is not really an option. And it gets really exciting when you think about beyond terahertz. So broadly speaking, we're following that 300K blackbody radiation curve up to terahertz, and all of a sudden things go kind of crazy after that point, which creates both opportunity if we could get there, but also it means we're dealing with some pretty exotic material challenges when we cross beyond the terahertz range. That was a self-indulgent digression. Let me get back to 6G. Now I mentioned that the very first parts of the 6G flagship are to get 5G deployed, and not just as now, not just the current release of 5G, but to get that evolution going, to look at the promise of 5G, the narrowband IoT, the LTE M1, the low power Bluetooth, and all of these other aspects humming along. But the group have also been working on these thematic white papers, and this year they were released actually just a couple of months ago. And they are hot off the press. The link is there on the right-hand side, and they cover the drivers, the validation and trials, the machine learning, networking, broadband connectivity, RF spectrum, connectivity in remote areas, business, edge intelligence, security and privacy, critical and massive MTC towards 6G, and localization. As the chair of the scientific advisory, I've read, unfortunately, every one of them and helped to co-author 2 of them. But I really commend them to you. Now, the remainder of this presentation, and Paul, just call me out when we start to run out of time, is just to quickly tap on those white papers. The first one is back to that, why do we need it?
There's no hurry. There's no hurry, Ian.
Great, thank you. So the first one is, why do we need it? And again, reframing the conversation in terms of outcomes, and then trying to identify really how does ICT in all its aspects that we would see in a 6G network, but specifically the communications part of it, how does that help achieve the goals? And so the exercise was outcome indicators. All of those are available from the UN Sustainable Development Goals website. And then we started to break down what existing relationship is there between mobile communications or ICT and this goal, or these indicators. What existing indicators exist, and what other indicators might we develop which is specific to our understanding of what 6G would need to include in order to get to those goals. By the way, a small anecdote, I have been looking at the UN Sustainability Goals for quite some time, every standards activity is required to think about how the standards will help deliver on the goals. And during my course of conversation with many people around Australia, most people I've met don't know that Australia, well, first of all, the goals exist, and secondly, that Australia has signed up to these goals. So if you haven't heard of these goals before, it's a commitment that Australia has made to contribute to and measure Australia's movement towards those goals. But the resources available on the UN Sustainable Development Goals website are really quite excellent. And the white papers is the first effort that I've seen to start to map the impact of telecommunications and ICT towards those goals. But one of the things that comes out of it is that, first of all, it's pretty hard to do. Intuitively, it makes sense, but it's pretty hard to show the relationship between 6G and quality education. So we gave it a go, and we'll evolve the KPIs over time. And the UN Sustainability Goals are actually worth really taking seriously because they do create a unified view of what we want the world to look like in 2030. So many countries have signed up to these goals. And if governments are developing policy in aid of these goals, if standards organizations are developing standards and creating global markets in support of these goals, and if industries are moving into those opportunities because of those goals, a common shared view of those goals, they're worth understanding, and they're worth understanding the indicators, and it's worth thinking about how your own activities will start to align with those indicators. Now, I mentioned that every G, when it contemplates the next G, talks about anyone, anywhere, anytime. And 6G is no different, except we go a little bit wider. We talk about intelligence everywhere, data everywhere, retrieval and storage, sensing everywhere, actuating everywhere, processing everywhere, and connectivity everywhere. So that connectivity everywhere is a goal which has really been challenging to meet, but it's been the primary objective as well as headline data rates of the earlier Gs. 5G took a really bold step towards enabling IoT and device-to-device or controlling smart devices, smart machines, smart factories. 6G really says there are more things that we want to be able to do. Sensing everywhere is a differentiator. So every device is a sensor. Trillions of devices means that we can sense many aspects of the world around us all the time, under all circumstances. But again, it creates that fundamental question about transparency, trust, cybersecurity, and privacy. White paper 2 talks about vertical services towards the 2030s, and really what do we need and how would we identify whether that would support different sectors. The target verticals: industry, mobility, health, energy, finance and banking, public safety, agribusiness, starting with potential business need. And then the question is, each one of these, what do they need in terms of the link data rate, latency, link budget, jitter, density, energy efficiency, reliability, capacity, and mobility? Now, what's on the screen is the result of consultation with different groups of industry, and it's guaranteed to not be right. One of the things we can say about predicting the future is we'll always get it wrong. The question is, what we come up with, is it still useful, or are we very far off the mark? And the only way to address that is, as we learn, as we start to understand how the industry is evolving and our health is evolving, let's keep testing those KPIs and also those key value indicators as we move along. We may never need mobility of 1,200 kilometers an hour in terms of a headline mobility data rate, or maybe we will. Maybe for the next generation of maglev trains, we really will need that. But from a high watermark, if that's what we're aiming for, then we can always recalibrate as we get closer to the actual business underpinned by a next G. White paper 3 is machine learning in 6G wireless systems. Again, an area that I'm particularly fond of. Part of what we've seen over the evolution of the Gs is the breakdown of the ability to centrally plan, model, and optimize mobile networks. When I worked at Nokia, my section was planning and optimization and configuration management. And as we moved from GSM to 3G, we suddenly realized that coverage was not the same as capacity, and the interplay between a high data rate user or a highly mobile user and a whole series of lower data rate users was no longer anything close to being linear. And the maths and the physics we had very soon started to be beaten out by measuring what was actually going on in the network, sucking everything in, carrying out optimization in big data, in data analytics, pushing back out and trying again. So, and where we've got data, we should use it to model, optimize, plan, localize, personalize. Where we don't have data, then we can still rely on the best physics we've got, the best equations we've got. But more and more, increasingly data-rich networks, where data comes from so many different sources, can be used to do a whole lot of things. We talked about, back in the days of 3G going to 4G, self-healing networks, which effectively means that you've got seamless connectivity. Something breaks in the network works around itself. You don't notice, your device doesn't notice, your autonomous vehicle doesn't notice, your robot doesn't notice. But all of that relies on not only a distributed way to understand operation of the network, but it also relies on a lot of real-world, real-time sensing using either specifically targeted data sets or secondary data sets to allow you to understand what's going on inside the network. The ability to process all that data relies very heavily on an intelligent network with different levels of intelligence, highly distributed, and in some cases where we don't know what the optimum outcome would be. So these GANs and data synthesized GANs are a really interesting way of thinking through how you might deal with those range of alternative different ways of doing local optimization. Of course, we can't have a 6G network without thinking about networking. But one of the fundamental aspects, we've talked about this for a very long time. We talked about software-defined radio, actually way back when I was doing my PhD. Please don't use that as an indicator of my age. But now we've been talking more and more credibly about softwareization of the network itself, and more of the network being a cloud environment, as opposed to specifically dedicated boxes which are specifically dedicated to one particular task. And we have for quite some time had an IP architecture. It just became the norm in 4G and certainly in 5G. But as all of those aspects become generic bits of hardware, generic cloud type IT devices, we still have some quite specific telecoms technology which relates to the radio bit and which relates to the things that we talk about with positioning. So high precision end-to-end telemetry and cross-segment analytics for autonomous 6G brings the slight but important difference from the evolution of a telecoms network to being an IT network, brings back the telecoms aspect and the data analytics part required to operate that network. So some of the trends we've seen just continue, but the ability to deal with that physical layer RF signal transmit receive still keeps evolving and is one of the fundamental areas for research and development in the 6G program. But the softwareization that we've been seeing continues in the thinking around 6G. Now again, back to thinking about the radio sides of things, there are some really big steps forward that we need to make in order to deliver on some of these data rates and the precision and the capacity per cubic meter. It's interesting that we're now specifically talking about capacity per cubic meter. We've seen with 5G increasing use of MIMO, multiple input, multiple output, and the ability to shape beams, the ability to deliver high data rates precisely to an individual, relatively precisely to an individual, or more precisely than we've ever been able to do. Now we're talking about holographic levels of multiple input, multiple output. And that means not just more antennas and more finer beams and more spatial selectivity, but it also means bouncing this signal off that MIMO system over there to capture a different perspective of your device or your user, and literally the ability to create three-dimensional images of the device, the conversation, the context, and use that to deliver more personalized services. It includes the use of intelligent reflecting surfaces. If energy is an issue, if interference is an issue, then the ability to intelligently reflect surfaces, or intelligently reflect radio signals, rather than just relying on what nature gave us with our coefficients of reflection and our multipath components. We're now talking about much more sophisticated shaping or trying to build signals which not only allow that holographic radio, but also allow us to reduce, suppress multi-user interference in a very dense environment where there's lots of different sources and different scattering of radio signals. And scalable cell-free networking, integrated access and backhaul, integrated space and terrestrial networks. All of these things have to move a substantial way forward in order for us to deliver on those KPIs that have been described. Terahertz communication, another big one. So I deliberately showed you the absorption spectrum up to terahertz. It is really exotic territory. Also, if you've ever tried to build even an E-band transmitter, you realize that your beam is laser-like. Terahertz, of course, takes that even further. So the ability to deal with vastly different physical Fresnel zones is something which requires not only different receiver structures, but really quite fundamentally different ways of packaging them together if you're going to try and operate across a range of different frequencies. And then on top of that, of course, once we get out of our physical layer, we get to our network friends, the protocols and the algorithmic levels required to cope with this vastly different and much more interesting and exotic and non-orthogonal physical layer means that we're starting to do some really serious work in actually making sense of the bits that we're sending around. I'm excited about that bit myself. So again, talking about what do we mean in terms of KPIs, comparing 5G to 6G, headline data rate is what we always use. So 20 gigabits per second to a terabit per second, but that's great. And we could probably keep doing that by combining different streams and becoming more and more parallel, which is what we have historically done with orthogonal frequency multiplexing. But the experienced data rate, not just a headline data rate of a gigabit per second, is a pretty phenomenal step forward. Spectral efficiencies, which go well into the exotic modulation methods, and the maximum bandwidth, there's a spelling mistake there, maximum bandwidths of 100 gigahertz and so on and so on and so on. But it's the latency, the reliability, and also the energy efficiency which really start to differentiate 6G from 5G. I mentioned that it may get to the point where the total energy budget of the planet that we consume to transmit bits, to make phone calls, to do data processing, becomes unacceptable. If we look at the footprint of data centers and search engines and data analytics around the world, it's starting to become noticeable. Just as the energy consumption around mobile phones started to become an issue over time, we're always looking to extend battery life. When we start talking about expending potentially not just gigawatts of energy to drive mobile networks and to drive phones, but we start talking about, for example, petawatts of energy, all of a sudden that energy consumption per bit starts to become a pretty serious issue. So we've been looking in the 6G program at zero energy consumption receivers, so they consume no energy until they get activated, but also looking at energy targets of 1 terabit per joule. Now, a joule, if I remember correctly, is what it takes to raise 1 gram of water through 1 degree Celsius at room temperature. Please forgive me if I got that wrong. Getting a terabit transmitted for that same amount of energy is a pretty ambitious goal. Latencies of 100 microseconds start to enable much more precise haptic type environments, and reliability, where in my day, again, when I was doing my PhD, we talked about fixed data rate, bit error rates of 10 to the minus 5, or packet error rates much less than that, much worse than that. Now we're talking about reliability of 1 in 10 to the minus 9, whether it's a bit or whether it's a packet. So each one of those different KPIs potentially can drive a new business opportunity, a new business solution, such as user-centric cell-free massive MIMO, but it also creates the research questions. And this is the attempt to map from the business need to the KPI to the 6G solution to that business challenge, and then creates the research questions, and that's directing the research of the flagship. And again, spectrum, my favorite bit, and again showing you that what the absorption profile looks like as you move towards terahertz. It's really exotic, and that if you can see the vertical scale on that axis, that little graph down the bottom, when we get to terahertz, we're talking about 1,000 dB per kilometer, which is, of course, if you think about a satellite link being maybe 100 dB, maybe 120 dB, of attenuation, there's no way you can go very far if you've got 1,000 dB per kilometre, which means that how we use spectrums looks very, very different. There's no way we'd use terahertz in a backhaul network, except if we did some really exotic things to narrow that beam and to deal with a whole lot of different sort of circumstances. So there's some great technology challenges around just building the by CMOS to operate in terahertz. So something affordable that operates in terahertz, using graphene, using analog modulation. So moving away from all the great work we've done on digital, moving back to analog, going beyond terahertz into visible light communication, and thinking about how you package all of that onto a device, whether it's an IoT sensor or whether it's the thing that you're now, I'm going to say holding in your hand, but it may not be holding in your hand. It may be the thing that's somehow connected to you and still enables that high efficiency, very low energy consumption use of broadband communication in the sense of broadband that we've never used to date. So again, some great research challenges, and the folks are really doing some great stuff with their silicon, germanium, and other such labs. This is one it's interesting in that it's finally really come to 6G. So when I first went to Finland, I said satellite communications, Australia being a big country, lots of people not living in dense urban environments, the response I got was not really interesting, simply because Europe, which was very much driving the 3GPP program at the time, is relatively densely populated. There's not a great deal of distance between most urban environments. There are some, but it wasn't a big deal. Now it's becoming a big deal because we're truly talking about global communities being connected. And if you think back to those UN sustainability goals, if access to communications and internet and educational sources will drive some of those goals, and if governments are investing in those goals, if the UN is investing in those goals, then it becomes really important to genuinely think about a global community. The response to COVID could also be enabled by, understood by, helped to be better propagated by access to truly ubiquitous communications. So the thinking now is we're talking about islands. Whenever you look at population distribution or mobile user distribution or sensor distribution, now thinking that it's not just people we're talking about, you can always draw a circle around something and say, this is a type of island. Different levels of density, different levels of spectral use, different levels of energy availability, but they're islands. And so by thinking about the entire world as potentially a series of islands which can be connected by different sorts of backhaul, whether they're satellite, obvious solution, but not exactly inexpensive, versus stretching fixed line communications or using some sort of relay technology, there are now many, many more ways that we can think about connecting these different sorts of islands using different sorts of backhaul connectivity. A really interesting area to stay focused on. We're getting close to the end of the white papers, but white paper 8 looks at some of the essential choices for developing business for 6G. Now, we talked about global megatrends, an aging, urbanizing population, growing population with increasing demands for quality of life. No one wants to go backwards in terms of quality of life, but with a changing environment, with climate change, with a change in where we can grow food, where we can harvest food, where we can catch fish, and then thinking about the societal changes of a sharing economy, disruptive business models, in continued focus on individual users' rights, coupled with power of platforms, the capability, but also potentially even the rights of AI and human-machine interface and the regulation around those. There are some really interesting challenges. If we operate the entire future world in a digital twin environment, for example, are there digital twin rights that we need to take into consideration? If we continue to move down the path of climate change and are unable to do anything about it, and where we can grow food fundamentally changes, is there a change or a trade-off in our centralization of how we grow and gather food? Must we hand over to a different way of doing things? And we don't know the answer to a lot of these, but we do see global megatrends which are unavoidable. The CSIRO has done some great work on global megatrends, and that work has made its way into these white papers. Those are updated on a reasonably regular basis, and I definitely encourage you to read them. So when we think about the dimensions that we care about, security and privacy, digital value platforms, cognitive network management, core network, when we think about those architecture domains, and when we think about the aspects that we want to either enable or to ensure are in place, digital trust, or something as interesting as a hollow presence, then all of these different things, all of these different technology trends and enablers and the different domains we need to think about, we suddenly need to think about what else we need to do in that space, or what we need to drive in that space in order to deliver on the opportunities, all those different trade-offs, and look at how those different trade-offs interact with each other. And from that, we can identify opportunities, we can identify value, we can identify advantages, and they, coming back up from the KPIs and the tech, hopefully will come back to the 6G business models and how the different sectors, the different verticals can respond to those challenges, relying on the KPIs and the understanding of the trade-offs between those different aspects at different layers. 9 is around edge intelligence. So not at all surprisingly, if you create any centralization in a network of the sort that we imagine for 6G, you create a bottleneck. We've been moving to the edge. We've been moving to distributed processing and distributed capability, distributed data store for quite some time. 5G took a big step in that direction. That has to continue. So we cannot create any bottlenecks in the network. There will no longer be an edge of the network. If we create an edge, we create a bottleneck. We potentially create a central bottleneck. So that has all sorts of interesting aspects, including the networking aspect, the cross-haul networks, dynamic task allocation, liquid computing handover, that's a great term, energy management, data intelligence, cooperative intelligence, and again, it's impossible to imagine that the network can be centrally optimized or can be centrally planned or governed. It has to be local, and local always runs the risk of creating divergence, but with the ability for different parts of the network to essentially agree with each other, and while still optimizing locally, the potential exists not only for some really amazing research challenges, but the potential exists to create a network which can fix itself if something goes wrong. That self-healing component first imagined way back in 3G. Something that also very dear to my heart, the challenges for trust, security, and privacy. And it really comes down to a couple of fundamental factors. Now we're talking about not just device to base station to backhaul to base station to device. We're now talking there may be 100, there may be 1,000 hops along the way of various different sorts of quality and integrity and scrutinizability. So all of a sudden we're relying on very complex networks where individual components may be compromised deliberately or inadvertently, and we have a very distributed, non-centrally planned network. So the aspects of trust, I'm relying on this thing to do what it says it will do, and that reliance on potentially individually vulnerable components creates a real challenge. So the ability to think about the complexity of these systems and security, trust, and privacy in those very complex systems create challenges in their own right. But the one I'm particularly fond of, those of you who know anything about the work around privacy preserving data sharing, is how on earth can you guarantee that all the data collected about me used personalized services, which was once rows and columns, but is now where I'm looking, what I'm doing, possibly even the shirt I'm wearing, my blood pressure, heart rate. How do we guarantee all of those things used to make life better for me or to locally optimize energy consumption or locally optimize the services delivered? How do we ensure that my privacy is preserved, and what on earth do I mean now by my privacy? So today we have a challenge, and it's part of my everyday work life, is to try and ensure that with data sharing and use, we've got a measure for how personal and how sensitive. If you scale up the complexities of additional context in time, so when you are in space, where you are, in relationship, what you're with, what you're next to, as well as all the different ways of gathering direct personal information about you, about all of us, we've got a really exponentially compounding problem to think about privacy. And then if you think about the context that you're in, the combination of those different parameters plus other aspects, it creates a really amazing research challenge, but genuinely a real business challenge if we think about the way GDPR is framed. I've taken this problem to the international standards community, and it's fair to say that the world is more and more aware of the fact that privacy in a hyper-connected digital world is a problem. Getting close to the end, so take a deep breath, we're almost there. I mentioned that during the course of the Gs, we're now talking about massive machine type communication. So we already have, in 3G, we had refrigerators sending out, connected to the internet and sending spam emails about being Nigerian princes. So we had an Internet of Things of sort. In 4G, we have more and more devices talking to each other, cars talking to phones, a lot of different devices talking to each other. In 5G, specifically targeted, a myriad of different devices being able to talk to each other. 6G, the working assumption is that we're entering the realm of trillions of devices talking to each other. So the ability to ensure that we are able to deal with trillions, and trillions is a really big number, the ability to deal with trillions of devices with that dependability, that efficiency, the scalability, the security, privacy and trust, the throughput and the sensing, that's a very substantial challenge which will go well beyond what was contemplated in the world of 5G. And the last white paper touches on localization and sensing, another area that over the years I've spent quite a bit of time looking at. We know that the best localization is a consequence of not only a physical understanding of where you are, as given by, in this case, a radio signal, whether it be GPS or a waveform from your phone, but the best localization is a combination of different sources, which can be corrected by local absolute known sources, or can combine multiple different sources and come to a reduced area of uncertainty. The new enablers, though, are associated with many, many frequency bands of higher accuracy positioning algorithms, with inertial sensors, with dense arrays, and potentially even with quantum computing, means that we've got a brand new armory of things that allow us to identify where you are, when you are, and your context. Now, that means that a whole range of new opportunities can be created. That includes the ability to much more densely pack radiation into an environment. So you get yours, you don't get the neighbors next to you, and vice versa, which means that spectral efficiency in terms of bits per second per cubic meter go up dramatically. But we also, again, now have this really important trade-off of the understanding of privacy, security, and where you are and what you are. So, ladies and gentlemen, let me just back up. That is where I intended to leave it. There are, in the research program, there are another 10 years ahead of us. The flagship program will be producing devices, waveforms, test beds, a whole range of different steps towards the solutions envisaged by 6G. But it will also be testing those in the test environment. The 5G test network will not surprisingly become beyond 5G network, which will not surprisingly become the 6G network, and then possibly the beyond 6G network. The materials folks will be developing all sorts of interesting new physical layer devices. The radio teams will be testing new sorts of modulations and new algorithms and new positioning. The data science folks will be evaluating new forms of AI. And all of it coming together will be constantly tested against, do we really need a terabit per second? Would you really have a business case for a terabit per second? Beyond vanity data rates, beyond the ability to claim I've got the highest data rate, fundamentally the investment in 6G will only be made possible if there's a business demand, a consumer demand, a societal demand, or perhaps through the lens of the UN sustainability goals, a global demand. That's me done. Thank you very much.
Thank you very much, Ian. I clapped on behalf of everybody. And I just want to check if David McKechnie is still online, because he has a question. David, are you still there? Ian, if you've got a moment, then could you please have a look on the chat service? And because it's quite an extensive question that David had, and he indicated he might not be here anymore. And you need to read it. I can't just read it out. It would be too difficult.
Mm-hmm. Right. Okay. So David's raised exactly the issue that I mentioned. So whenever we envisage an XG, we always say, okay, what our starting point is, what did we not get into this G? What did not actually materialize? And the statement that there's a lot similar to the 2015 Next Generation Mobile Network white paper on 5G, other than the harder targets, is absolutely true. So I remember when 3G was being contemplated, and I believe it was Future Land Mobile Telecommunications Platform, FMPLTS. Someone will remember what the actual acronym stood for. And then it became UMTS, and then it became really 3G. We said ubiquitous, anyone can access anywhere, anytime. And so I think it's fair to say that we're seeing that exactly again. So it's a fair pickup. The difference, though, is that we now, every time we launch a release, or every time we put out a release, even if not too many manufacturers are manufacturing massive MIMO systems, we know it's possible. We know the work has been done, so we recalibrate the baseline, which means then that we can, from a research perspective, say, all right, 10 times less, or in some important areas, 3 dB more. So that's the sort of traditional research response. But what's different in this case is there's really an attempt to try and understand how business might use, how society might use those different parameters. But with one eye closed and squinting a little bit, you can see exactly the same trend as all the other next Gs. Paul, is that a reasonable answer to the question?
Yeah, and it's the good thing is that your answer is recorded, and David can listen to it, and if he has any further questions, then he can come back. He could come back to us, and we will send you his response if necessary. A couple of other questions, Ian. Jeff, in the first masterclass, mentioned that the mobile technology, the wireless technology, as we are talking about today, might not be the right technology for example, for autonomous cars. And he was talking about more like laser-like technologies. And when you talked about your terahertz spectrum and beyond, you actually also mentioned the word laser. Are we seeing something happening there in that respect? Is Jeff right that it's perhaps too difficult to get wireless technology? In any case, not in the foreseeable future. Do you think that is still possible? Is laser an alternative? What are your thoughts there?
So if it was Jeff Hayden who said it, then he's right. Whatever Jeff says, I'll just agree with as a starting point. I've had experience with E-band, and E-band is certainly nowhere near as exotic as terahertz, but and it was used for, actually, from time at CSRO when Jeff was also there, trying to get backhaul made with E-band, and ultimately CSRO developed some tech licensed to a company in Queensland, sold to the US, and getting backhaul E-band to work was remarkably challenging simply because of the pointing problem. So literally trying to point the transmitter at the receiver with a really fine beam. Now that required some really sophisticated tracking. Once it was in lock, it tracked, but it worked. As we move up the spectrum, then that problem accentuates quite dramatically. But there's something interesting that happens. So we all know that visible light communication was an interesting idea some years ago, but now it's being seriously considered in public transport systems and being seriously considered in a range of different areas. I think the combination of MIMO systems and exotic spectrum, we don't really call visible light exotic, but in the radio world, as we start to get under that upper end. There may well be something in that. It would be near impossible to try and align a wafer-thin beam if you were trying to use a mobile device on a public train. There's so many things you could think would go wrong with that. But if we had a massive MIMO system where MIMO was not 5 by 5 or 10 by 10 or 20 by 20, but if it was a million by a million, the potential exists that some of this really exotic stuff could actually work. And the reason that gives me some, that I'm willing to say something as bold as that, again, back to CSRO days, we all know that if you want to minimize interference between antennas, you separate them by more than half a wavelength, and that's all good. But the folks that developed the checkerboard array for the square kilometre array Pathfinder project deliberately had the antennas packed close to each other in this little checkerboard and just dealt with the interference because they had sophisticated signal processing behind the radio. So I think some of what we know as conventional wisdom may break down because we can throw spectacular amounts of processing at it, and we can throw spectacular amounts of different elements at it. So this is a very long-winded way of giving you an answer. I think if we kept doing things the way we have been doing, we very quickly will hit the wall of impossible. But if we learn from some of the different sorts of things that we've done and combine them, we may well get back into the game of possible.
Yeah, I think it was all these, all the developments, you cannot go in a linear way, you have to quantum jump in order to move forward. And talking about quantum, you never know what comes out of that, that we can use in quantum communication or things like that. Still, very uncertain, but not the impossible if you start looking over longer periods of time. Ian, the next question is, you mentioned the totally different business models for 6G, that because of things going to the edge, the whole sort of situation about privacy, etc. So then you actually start looking at, call it the OTT business models, the over-the-top business models. And we've all seen what happened there, with the Googles and Facebooks of this world, So what's, what do you see happening in that area? Will it be monopoly? Will there be the potential that companies monopolize that in the way that we've seen that happening on with the current digital companies?
Yeah, so there's always the opportunity for monopoly in an environment which is which supports it. So if we think of this a little bit like the new internet, so now we're not talking about web pages and searching and such things. We're now talking about a network being a source, multiple sources of information, and multiple different pockets of value. Whoever can aggregate and distribute and shape and optimize that data and value has the potential to be a winner-take-all if the system allows for it. So the lack of centralization means that organizations could grow quite rapidly. So once upon a time, if you were the Telstra or the Vodafone or the Optus, it was your walled garden and you decided who played. Now this is almost completely unwalled garden. There are little walls around the place. But so it means then if you can aggregate and create value, then, and you have an implied or a practical arrangement with value creators and data creators, then you could really do what we've seen in the browser wars. It starts to become a winner-take-all, a couple of dominant players, and everybody else falls away at the wayside. That's always then the regulator's dilemma. How do you allow a market to flourish and allow that healthy competition, but when it gets to a relatively small number of players, what do you do? The most important thing, I think, is to understand that's possible and then decide. If the environment was such that you must not ever allow this to happen, then that potentially stifles creativity because we don't know all the value that 6G will create. If there's no regulation and no one pays any attention whatsoever, then we run the risk of the sorts of things we're starting to see with the big social media brands, where retrospectively, after they've gathered 1 billion users or 2 billion users, retrospectively legislation or regulation, or even in some cases some harsh penalties are coming down. So being ahead of the game in terms of understanding the different surfaces, the different vectors, the different potential, I think puts us in the best place. But so again, another long-winded answer. The short version of it is yes. The long version is, if we're aware of it, then we can watch as the pot starts to warm up and decide when we want to jump out as the frog, or when we want to do something to lower the temperature.
I think, if you look at the current sort of, and I come back with a question on that, geopolitical situation, then I would think, and I would suggest that your flagship organization should, really start seriously looking into this as well, and, have some people thinking about it and start, talking about it, and also with governments, etc. Because we have, the technologies, this 6G, but also artificial intelligence and things like that, they are going to have such an enormous impact on humanity and on our world, yeah, that apart from the technical issues, we at a much more earlier stage than when it's too late, yeah, have to start at least addressing, options and possibilities and a vision and some strategies, if these technologies are arriving, what are we going to do with it? Is that something that your flagship organization is looking into?
Yes, one of the things about the Nordics is they're very societal centric. They're very humanist. Might not seem so, but they're very, very concerned about the impact on society. So the reason that the flagship goals were framed in terms of societal outcomes is that's the goal. So we've got some pretty impressive researchers and developers and engineers who've got very impressive credentials, but the whole conversation is framed around what's the impact on society. And that's both from the enabling telehealth sort of questions to, is this having unintended consequences? And it's always difficult to try and understand unintended consequences. So it's nearly impossible unless you talk about it with a particular time frame. The unintended consequences of improving vehicles, improving cars, includes traffic jams, it includes air pollution, includes road deaths, includes a whole range of things. But at the time, it was a safe way to get around, and there were all sorts of benefits. The reason for framing the 6G flagship, or aligning the 6G flagship with the 2030 UN sustainability goals, is that it gives us a point in time. It gives access to a whole lot of thinking about where things might otherwise go, and also gives an agreed set of outcomes that we say we want. And when I say we say we want, many countries around the world have signed up to them, including Australia. So we have said, yes, we want the world to look like this, and this is how we'll measure it. So winding back to the flagship folks, the reason that the first white paper was around impact of ICT and telecoms on the UN sustainability goals is to try and genuinely keep our eyes open that these are the sorts of outcomes that we're trying to help create, and the adverse equivalent of those outcomes are things we're trying to avoid. So, and by constantly bringing back every research proposal, question, and testing them against those frameworks, means that there at least is a way of trying to align what we're trying to achieve with research work that's being done on bits and bytes and bits of CMOS.
The link to that is a question: can the current geopolitical sort of situation just makes the introduction of 6G impossible or very difficult, and you talked about, the global sort of developments, but at the moment at least, it looks far more like islands, like, a Chinese island and a Western island and a Russian island and a North Korean island and whatever, yeah?
Mm. Yes, it does. So this is unfortunately not just a problem for the next G. It's a problem for the world of standards in general. It's a problem for interoperability in general. The world of standards and the world of the Gs are, of course, very closely connected, because you can't have the next telecoms G without really getting a solid agreement around the standard space. We're also So just staying in standards for a moment, we are certainly seeing geopolitical tensions start to play out in the standards world, because if you are first and best with the standard, even if it's shared globally, then you're in a great position to capitalize on the tech that ultimately gets deployed. You know it better, your manufacturing is more ready, you're more willing to take it on. So that's a really big question, Paul. And
yeah.
the only
Not
answer
easy to answer. Yeah.
the only real answer might be, even if the islands, let's see if I can stretch this analogy, if the islands are becoming more clearly separated, we might have a fundamental level to interact, which is at sea level, which everybody can agree on, and then we all build value in our own little island. Probably overstretch the analogy, but you can build your own flavor. You could build your own flavor of 6G. Of course, that's what did happen with 3G. The time synchronous CDMA that was developed in China off the back of the wideband CDMA in Europe and North America created a flavor of 3G, which was China specific. That may well happen again.
Yeah. Ian, a question from Matt Schultz is what is the significance of this technology in the context of a smart city?
I would be disappointed if Matt had not asked that question. So the many aspects about smart cities rely on the ability to create digital twins and to plan, model, optimize those digital twins. A lot of that digital twin thinking is being done. And again, I'm going to say the world of standards and see how many people stay on the call. There's really great work being done in that space. But to build the twin, it relies on access to data. And that data is not only this is what's currently going on, situational awareness, but also a whole range of secondary sources that allow you to do root cause analysis or what if scenario planning or a better understanding of how things are actually operating. At the moment, we are reliant on sensors we build into systems or data that we deliberately flow into those digital twins. And any use of secondary data or exhaust data is something which still takes quite a lot of effort. The intention is that everything is a sensor. Everything that can generate a signal or receive a signal becomes a sensor. And those sensors get used for a very rich tapestry of data sources which help understand what's going on, who's moving where, and help to create, through individual points of light, helps to create a vibrant digital understanding of how a city is operating. How that then gets used is very much dependent on what we allow to happen. So again, going back to the standards world, there are models being created at the moment for city ICT platforms. And whilst we don't all agree what they look like, again, an island problem, more and more of those will start to become a standard, maybe version A, version B, or version C, take your pick your standard, but still there's a standard way of doing it. And so the ability for all of this data to feed into an ICT platform means that you can shape, take advantage of predefined digital twins, or you can start to create really rich understandings of the situational awareness, the prediction, the what if, or augmented digital twins. So in order to be smart, in order to have a smart city, we need digital twins. In order to be able to understand what's happening in that smart city, we need to be able to exercise these digital twins. In order to optimize something in a smart city, we have to have the ability to close the loop. And that closing the loop might be as simple as changing lights on a multi-lane system, saying this lane is now that direction, or it might be the ability to do something fundamentally different so that you don't need to drive to work, or you don't need to take this particular pathway, or if there's a pandemic, this is all the information you need to know about doing things differently. Again, I'm sorry, Paul, a very long answer.
No, fantastic. You know, these are complex issues, so it's good to get an extensive answer. Michael Riley, are you online? Could you please unmute yourself and ask your question to Ian?
Thanks, Paul. And thank you for sharing your insights. Just a very simple question. We're currently struggling with the interconnectedness between 5G and fibre backhauls. I sense it's going to get a lot harder with 6G. With that proliferation, that magnitude change in devices and sensors, what do you think that will, how will that affect the requirement for fibre networks and backhaul?
So thanks very much for the question, Michael. I'm not a backhaul specialist, but I'm going to have a crack at this nonetheless. The easy stuff is the capacity that you need. So if you can keep scaling up. Fibre, so far we haven't yet found the maximum amount of bits per second we can squeeze down to fibre. So capacity is not the problem. It's the interconnection which is the issue, and it's the diversity of interconnection. Again, I'm going to hope that standards come to play here. I was talking recently in the standards world about smart grids, and we talked about the technical functionality of doing demand-side energy management. So there's a shortage of supply, excess demand expected. Can you shape demand in the network? And from a technological perspective, they said every step we could probably do. There's a little bit more work to be done from a functionality perspective. From a interoperability perspective, they said we really have problems because, not surprisingly, vendors try to ensure that you get locked into their kit. And that's certainly been true in the telecoms world for quite some time. And then there's a security aspect and a privacy aspect, which haven't really been developed as much as they should be. In the world where you've got probably measured in billions of different sorts of devices, no one has any hope anymore of trying to keep their interconnections proprietary or to have very exotic extensions on existing interfaces. So again, I'm going to come back to standards. The ability to agree a fundamental set of plug and play type interfaces, which if you happen to speak to another device which has that extra capability might work, but in practice it's too dangerous a game to play. If we don't head down that path, I think we're ultimately doomed. And I think people realize that the game is not going to be about creating exotic sensors for exotic networks. It's going to be about building value on top of them. I hope I didn't confuse things more.
Michael, any further reaction, comment? Are you happy with Ian's answer?
Well, that's the best answer I've had to date so far, Ian, so thank you. I understand the drive to standards and interoperability, and I'm encouraged by the wireless operators in America sharing infrastructure. They consider themselves marketing companies, not infrastructure owners.
There you go.
But I'm just struggling with, in the world of councils and property development, we're just struggling at the moment working out which street poles to put fibre to. Now, if we've suddenly got 1,000 more sensors in between each street pole, where do you lay the fibre? What's the actual practical implications of where you put your networks, your fibre networks? You can't dig up roads for the rest of our lives to do this stuff. We got to do it now and accommodate the next 2 decades.
I agree with you. You and Matt Schultz should connect, and you should rail about this issue over some beers, because it's real. There is a real connectivity challenge, not just in Australia, in many parts of the world. It's a real connectivity challenge. Fibre gives us a superhighway for at least another G or 2. As I said, we keep finding ways of putting more bits per second into a fibre, bits per second per hertz into a fibre, and it's phenomenal, absolutely phenomenal. But if they're not in the ground, if they're not connected, then that's a really interesting point, but it's not that useful. So that retrospective upgrade of the optical superhighway is the big investment that we have talked about in Australia for at least 10 years. We almost kind of sort of got it, and now, of course, it goes well beyond the fibre to the home conversation. It's fibre to the street lamp conversation. So that's not going to be fixed by 6G, but there is something that's worth considering. There was once upon a time some technology called ultra wideband, which was really popular, and it was 3.6 to 10.5, 10.9 gigahertz range, unlicensed, short range communication where you could pump out a gigabit per second, or you could put out 10 kilobits per second, depending on how you modulated your signal. So what it meant was, effectively, you had a whole lot of these different devices with unbelievable capacity that could just plug in. Signal doesn't go very far, but they plug in, and not very far means tens of meters. So if we had that, if we had an ultra-wideband solution that's now being recontemplated for 6G, then you create an island, a wireless island, covered by that ultra-wideband, and then you plug into one street lamp, and the rest of them just talk to each other. That's at least the principle. And ultra-wideband, it worked. It was real. In the US, it was allowed up to, I think it was 100 milliwatts, if I remember correctly. And no, that can't be right. It was under the Part 15 unintentional radiator limit, so it was well below that power level. But we built devices which worked, and then in Europe they said actually it has to be 1,000 times less powerful, so 1,000 times below the unintentional radiation limit, and it got killed off in anticipation of 4G being rolled out. It's back on the table for 6G, so there may well be a genuine wireless solution to create an island that means you only need to plug into every 100th lamp pole.
Thank you very much, Ian. I think we will let you go. You know, we're now talking for more than 1.5 hours, so it's fantastic to get your insights and your incredible knowledge about this topic. So a big thank you from all of us for a fantastic presentation, but also for the answers on complex questions. And we're looking forward to also for everybody, the delegates, you know, there is a link. Mark already put a link to the slides on the chat. There will also be shortly will be the YouTube video will be finished, and Mark will make that available to you. So I also, because this is the last session of 3, I actually, because of the bit of an turmoil in the beginning of the presentation with noise, what I of course did forget to mention was that Ian is also the president of the ACS. So you know, it's thank you to your organizations and to Matt's organization ESCA for organizing that, and on behalf of the 2 organizations, we would like to thank all the delegates for their participation and for their questions and for their interest. And we hope that you have found this interesting. Please support the 2 organizations. They really are looking after your interests, and share any feedback. Mark is really interested in hearing back what you thought of this. We got already a few good comments on the chat, and thank you people for that supportive comment. And that's important for both organizations to also plan future events. On that note, Ian, once again, thank you very much. Mark, thank you very much. Delegates, thank you very much. And I hope you all have a good evening. Thank you very much. Bye.
Thanks, Paul. Thanks, Mark. Thanks all.